Our next speaker is Pierre Bellec.
Hi everyone. I'm going to talk about sparse linear regression and the lasso and the regularization path of the lasso. So I'm considering the classical sparse linear regression setting. So I've got a design matrix with the columns that I may call the covariates. There is a ground truth beta star, which is unknown, and which is hopefully sparse. And I consider this model. I observe a vector y in Rn, and my goal will be to recover x beta star. And I put some Gaussian noise. And the superstar estimator in this context that has been studied heavily in the last 10 or 20 years is the Lasso, which in its penalized form takes this form. So we penalized the least squares criterion with the L1 norm, given the tuning parameter lambda. It appears that this Lasso estimator enjoys something that has been called a regularization path. So it comes from this paper by Efron et al., which is the last paper, so least angle regression. And so it appears that there is a finite set of tuning parameters. So the first is the largest one. And so for all tuning parameters larger than lambda naught, the Lasso estimator is 0. So the support is the empty set, and there are no active covariates. And at the first knot, at lambda naught, one covariate enters the Lasso, enters the active set. So the support contains one covariate, and the active set, the active covariates contain X3 here. And then another, at the next knot, another covariate enters the Lasso, so the support gets bigger and bigger. But what may also happen is that a covariate leaves the Lasso, and so here X4 leaves the Lasso and the support is reduced. Right? And the big finding of this paper, this last paper, is that the support of the Lasso is constant between two knots. And if you Google image Lasso path, you find a bunch of pictures like this. So what is that? So horizontally you have the tuning parameters. So here the tuning parameter is really big. There are no active covariates. And as it decreases, some covariates enter the active set. And if you look at these particular covariates here it enters the Lasso, the active set, and here it leaves the active set. Okay, so our goal in sparse linear regression will be today to upper bound the prediction error of some estimator Fhat by some benchmark. And the most common benchmark in this setting is the min-max rate, which is given by S log P over S over N. And has been heavily studied, and several different methods can achieve this rate. For example, there's this exponential screening estimators that aggregates 2 to the P different least squares estimator. And there are also L1 regularized methods like the Lasso or the Danzig selector. But today I will be more interested into other benchmarks. Like, can we mimic the performance of the best Lasso estimator? So this is this benchmark here, which takes an infimum over all possible tuning parameters. And this is the prediction error of the best Lasso estimator. Another benchmark that would make sense if we believe that L1 regularization is going to solve the problem would be the constrained Lasso, where here we constrain the beta parameter over an L1 ball that has exactly the radius of the truth. Of course, this estimator is not accessible in practice because you cannot use this parameter because beta star in L1 norm is unknown. So why this benchmark would make sense? Well, these papers have found that the prediction performance of Lasso under correlations can be substantially better than the universal parameter if we can choose a lambda depending on beta star that is smaller than the universal parameter. So this is why this benchmark would be useful in practice. Okay, so some notation before stating the results. So a support will be a set T, so it's a subset of 1P. And from a support, I can construct the orthogonal projection on the linear span of the covariates in T. So there's a typo in this line. So this is the projection of Y minimizes the L2 distance over the span of the active covariates. And F hat will be a set of support. So if I come back on the first slide on the regularization path of the lasso, you could think of F hat as a set of plausible active sets, of plausible supports. So if you look at the regularization path of the lasso, at every knot you get a new support. So for instance, F hat would be the set of all the supports that appear on the regularization path of the lasso. Right. And then I'm going to study a selection procedure. So I minimize over all the support in this set of support, which could be, so this set F hat could be completely data driven. Its cardinality can depend on the data, and all the supports here can depend on the data. And to select a support among these, I'm going to consider this penalized criterion, which is the least squares criterion, and penalized with some complexity criterion, which is very close to CP, AIC, BIC, and their variants. So this is actually the selection procedure that was suggested in the original last paper, and then on the following papers on the degrees of freedom of the lasso. But to my knowledge, there is no statistical guarantees on the performance of this selection procedure. And so once we have selected one support, we use the projection of Y on this support as a prediction for X beta star. So here's the first result with this selection procedure. So this is the same selection procedure that was displayed in the previous slide. Then with high probability, we get this oracle inequality, or we get this guarantee. So on the left-hand side, we have the performance of our estimator, which is constructed with the selection rule. On the right-hand side, we have two terms. The first term is the best prediction performance in the set F hat, and this is the complexity term that defines defined by the size of T. Right. So here it's the best approximation of X beta star in the span yielded by T, and what's unexpected in proof and in that result is that the randomness of F hat, the set of supports that you give me, doesn't matter at all. And the proof outline is actually very similar to previous results. And the trick was to realize that we could completely decouple the randomness of F hat from the rest of the problem. And so what's a natural application of this? Well, what do I obtain if I plug all the supports that appear on the regularization path of the lasso into this F hat? So this is the next slide. So I complete all the regularization path of the lasso. I set F hat to be all the supports that appear on the lasso path. I select a support with the same selection rule as before. And I use this estimator, which is the projection of the selected support. Then with high probability, I obtain an oracle inequality with, on the right-hand side, an infimum over all tuning parameters. And so this is the performance of the lasso estimator with parameter lambda. So somehow, if there is a lasso estimator that has a good prediction performance and is sparse, then my procedure will get a very good prediction performance. And under the usual assumptions that we make on the design matrix, so that to have theoretical guarantees for the lasso, we obtain similar bounds. So from a theoretical point of view, it will be a good idea to use this procedure instead of lasso. And the result is actually more general, because you could, instead of plugging the supports that appear on the regularization path of the lasso, you could actually plug any nonlinear or linear estimators and plug their supports into Fhat, and you would obtain a similar oracle inequalities. And I'll stop here. Thank you for your attention.